Hi, in this video, we are going to continue our study of number theory. And today's video will be a problem solving session. We'll look at a few of the divisibility problems and the techniques used to solve problems like that. So let's begin. The first one is this one to say, show that 39 divides 7 power 37 plus 13 power 37 plus 19 power 37. We have to prove the divisibility of this expression with 39, right? So a common technique in solving problems like this is using binomial theorem intelligently. So we have 39 here. In order to prove that this expression is divisible by 39, I can say that 39 is 3 times 13, right? So if this expression is divisible by 39, obviously it must be divisible by 3 and must be divisible by 13. Correct? So let's try and check whether it is divisible by 13, right? That is the first step. So how do I do that? So notice that there is a 13 power 37 plus 7 power 37 and 19 power 37. And 7 and 19 are special because we can write it like this. 7 is 13 minus 6 power 37 and 19 is 13 plus 6 power 37, right? So basically what I'm trying to do is write the whole expansion in terms of powers of 13. And you have a minus 6 and a plus 6 in these two binomial terms, right? Now, obviously, we know how to expand it by binomial theorem. Here, when you do that expansion, you will realize that you will get terms like 37C0, 13 power 37, plus 37C2, 13 power 35, and 6 power 2. All the even terms will be left. The final term will be 37C36, 13 power 1, minus 6 power 36, right? And the other terms, the odd terms, will get cancelled because they will have alternating signs, right? You will have 37C1 will come with a negative sign, but in this one, 37C1 will come with a positive sign. So the odd terms get cancelled and you have this stuff that is left here. So, and this stuff is left here with a double. So twice of this. That is the expression that we get when we add these two, right? You can see clearly here that every term is divisible by 13. Even the last term here has a factor of 13, and this term definitely has many factors of 13. It's 13 power 37. So the sum of this and this is definitely divisible by 13, and you also have 13 power 37 is already divisible by 13. So what we have shown is that 13 divides 7 power 37 plus 13 power 37 plus 19 power 37. So that is confirmed. Now what we have to show is 3 divides 7 power 37 plus 19 power 37 plus 13 power 37. We have to prove that this is divisible by 3 as well, right? So how do we do that? The way to think about that is express each of these terms as binomial expansions of stuff that is divisible by 3, right? We can write 7 power 37 as 1 plus 6 power 37. And we can write 19 power 37 as 1 plus 18 times 37, power 37. And similarly, 13 power 37 also can become 1 plus 12 power 37. Now, when you expand it by binomial theorem, this will look like this, 1 plus 37C1, and this is 6 plus 37C2, 6 square, and so on. And finally, you'll get the last term 37C37, 6 power 37, right? And similarly, here also, you'll get 1 plus 37C1, 18. And last term would be 18 power 37. And here, you'll get 1 plus 37C1, 12. And the last term will be 12 power 37, right? So basically, what we are getting, all of these terms are divisible by 3. All of these terms here are also divisible by 3 because there is definitely a factor of 6 and 18 left here and 12 here. So the addition of all three, this is entirely divisible by 3. And you get something like 3 times some a plus 1 plus 1 plus 1 plus 3. So it is clear that it is overall divisible by 3, right? So by binomial theorem, we have proved that the expression is divisible by 3 and it is also divisible by 13, which implies that the expression must be divisible by 39. So that is our proof, and we basically use binomial theorem to do it. So that is one standard technique that you should be aware of. Let's go on to the next question. This says, show that for each integer n, for each integer n greater than equal to 1, the number n power 4 plus 2n cubed plus 2n squared plus 2n plus 1 is never a perfect square. Is never a perfect square. Great. So in order to think about it, you will have to first think of how to simplify this expression, right? That is the first step. So what we can do here is break down this expression like this: 2n cubed plus n squared plus 2n plus 1, right? So why did I do this? Because here in this term, I can take n squared common and it will be n squared plus 2n plus 1. And here you already have an n squared plus 2n plus 1, right? So the factorization of this is simple. It is n squared plus 2n plus 1 multiplied by n squared plus 1. So basically, this is n squared plus 1 multiplied by n plus 1 whole square, right? That is the number here. Now, if n squared plus 1 multiplied by n plus 1 whole square is a perfect square, if it has to be a perfect square, we must have, this is already a perfect square, right? If you have an overall expression which is a perfect square and one factor of it is itself a perfect square, then the other factor must also be a perfect square. So basically, we should say that implies that n square plus 1 must be a perfect square, right? Why is that so? Because already one factor n plus 1 whole square is a perfect square. So this must also be a perfect square for the whole thing to be a perfect square, right? Now, it is easy to show that this is impossible because n squared is less than n squared plus 1, which is less than n squared plus 2n plus 1. So what we have is n squared is less than n squared plus 1, which is less than n plus 1 whole square. So what we get from this is that n squared plus 1, the number, lies between the two perfect squares, n square and n plus 1 square. But n square and n plus 1 square are two successive perfect squares, right? Like the integer n and the integer n plus 1. If you take the squares of both, you get these. So what we have shown here is n square plus 1 lies between the perfect squares of two successive integers. So n square plus 1 itself cannot be a perfect square. If n square plus 1 itself cannot be a perfect square, then obviously this whole expression cannot be a perfect square. So that is the proof. The idea of the proof was factorization and then realizing that no perfect square can lie between the squares of two successive integers, right? So that completes the discussion. Let's go to the next one. Here we have to show that for each integer n greater than equal to 1, the number 49 power n minus 2352 times n minus 1 minus 1 is divisible by 2304. Now, first thing to notice here is try and understand the factorizations of 2304. So 2304 prime factorization is basically 2 power 4 into 13 square, right? So technically, probably not 13, not 13 square. It will be into 12 square. This is divisible by 12, I think. So think about it. 12, 11, 108. Yeah, it is divisible by 12. So you have, this is basically meaning that it is 48 square. 2304 is 48 square. And you can also realize that 2352 is equal to 48 times 49. These are just the values from the numbers itself. You can figure this out, right? Now, okay. So basically we have 49 power n minus 2352 n minus 1. So 49 I can write as 1 plus 48 whole power n minus 2352 n minus 1. So if you expand this, you'll get 1 plus nc1 48 plus nc2 48 square till you get ncn 48 power n minus 2352 n minus 1. This is the expansion, right? Binomial theorem expansion we have done for this, right? So you can see that the 1 gets cancelled here. And this is 48n, if you realize this. NC1 is n, so this is 48n plus NC2 48 square and so on, plus NCn 48 power n minus 2352n, right? So you should realize that 48n and minus 2352n will become minus 2304n plus, now notice these terms always have 48 square common. You can take 48 square common and you'll get NC2 plus NC3 times 48 and so on till NCn times 48 power n minus 2. So the bracket inside is an integer and 48 square is 2304. So you have minus 2304 n plus 2304 into some integer, right? So it is clear that this expression is divisible by 2304. You can take 2304 common, you get z minus n, right? This is 2304 something z minus n. So it is clearly divisible by 2304. And now, in general, the question can be generalized and you can show also that a minus 1 square will divide a power n minus a times a minus 1 n minus 1. You can prove this. If you put a as 49, you will be able to show 48 square is similar to 49 part. The question is a generalization. So a is equal to 49 will give us the question that we have already done just now, right? The proof of this is simple. You just have to write the factorization of a power n minus 1 as a minus 1, a power n minus 1 plus a power n minus 2, and so on till 1. And then take a minus 1 common and simplify. You should be able to get an a minus 1 factor even from there. So the simplification of this becomes basically a minus 1 common, a power n minus 1 plus a power n minus 2 plus a plus 1 minus an. This is the overall expression. Now you should realize that the bracket inside vanishes if a is equal to 1. If a is equal to 1, you should realize that there are n minus 1 terms here, 1 term here, minus n. So this is n minus n 0. So that means a minus 1 is a factor of the expression inside the bracket. Inside the bracket. If a minus 1 is a factor of the expression inside the bracket, we can take it as common outside and you get basically a minus 1 whole square into some expression, which proves that a minus 1 whole square divides this, right? So that is the general question and we have solved a particular case here. Let's look at the next one. The next one is basically a true and false statement. The first part of the statement is it true? Is it true that 3 never divides n square plus 1 for positive integer n? And the second part of the question is saying, is it true again that 5 never divides n square plus 2 for a positive integer n. Now, this is a question that you can solve if you understood the previous lecture that I made on this subject, which is the subject of quadratic residues. Now, if you think about it, modulo 3, the only residues possible are 0 and 1. Residues possible are 0 and 1 for n square. So quadratic residues for n square can only be 0 or 1 mod 3, basically. So obviously then n square plus 1 can only be 1 or 2 mod 3. So therefore, it is true that 3 can never divide n square plus 1, because it is not, n square plus 1 is not 0 mod 3, right? Similarly, if you think of quadratic residues modulo 5, what are the quadratic residues modulo 5? Think about it. 0 square will give us 0, 1 square will give us 1, 2 square will give us 4, 3 square will also give us 4, and 4 square will also give us 1. So these are the 3 quadratic residues possible, right? Now, if n square is 0, 1, or 4 modulo 5, then obviously n square plus 2 will be 2, 3, or 1 modulo 5. So if n square plus 2 is coming out to be 2, 3, or 1 modulo 5, then 5 can never divide n square plus 2, right? So that finishes off this problem. This problem is a direct application of quadratic residues. You need to go back to the previous video if you have not understood that concept, right? The next one is this computational question. This is an actual AIME exam problem. Okay? So what is the problem? 10 power 4 plus 324 multiplied by 22 power 4 plus 324 and 34 power 4 plus 324 and then 46 power 4 plus 324 and finally 58 power 4 plus 324. You have to calculate this divided by, and this time we start off from 4 power 4 plus 324 and then 16 power 4 plus 324. Notice that the gap between the numbers 10, 22, here also it's 4 and 16. And then it will be 28 power 4 plus 324. And then 40 power 4 plus 324. And finally, 52 power 4 plus 324. We have to evaluate this. Obviously, we cannot directly calculate anything. This is too long. So what you have to think of is some clever idea. So let's try to figure out a pattern here. So the terms are looking like x power 4 plus 324. So we can write that as x power 4 plus 4 times 81. 324 is 4 times 81. So let's put y as 3 and x can be variable basically, right? So you're getting x power 4 plus 4 times y power 4 here, right? Because y power 4 will be 81. You have x can vary, right? Now, if this expression looks like this, then we can factorize this expression by doing x power 4 plus 4 times y power 4 plus 4x square y square minus 4x square y square. And this will become basically x square plus 2y square whole square minus 2xy whole square, which can be simplified as x square plus 2xy plus 2y square multiplied by x squared minus 2xy plus 2y squared, right? And now think about this. This will become x plus y whole square plus y square. This is x squared plus 2xy plus 2y square. And the other term is x minus y whole square plus y square. Because that will become x squared minus 2xy plus 2y square, right? So basically, this is my factorization for x power 4 plus 4y power 4. Now, in this problem, we are just going to assign different values of x, right? X will be 10. Y is always 3. Notice every term in the numerator and denominator, y is 3. So if x is 10 and y is 3, we get here 13 square plus 3 square multiplied by 10 minus 3, 7 square plus 3 square. This is for the first term. For the second term, when x is 22, and y is 3. We get basically 22 plus 3. So 25 square plus 3 square and 22 minus 3. So 19 square plus 3 square, right? And similarly, we get 34. X is 34. So it becomes 37 square plus 3 square and 31 square plus 3 square. And then next time is 46. So you get 49 square plus 3 square. And you get 43 square plus 3 square. And last time is 58. So you get 61 square plus 3 square. And you get 55 square plus 3 square. The product of all of this is the numerator, right? And now if you look at the denominator, it is also in the same form, but it starts off with x is equal to 4. You'll get 7 square plus 3 square. And you get 1 square plus 3 square here. And then you get 4, then 10 comes. No, then 16. So you get 19 square plus 3 square. And you get 13 square plus 3 square. And then you get 28. So you have 31 square plus 3 square. And 25 square plus 3 square. And then you have 40. So you have 43 square plus 3 square. And 37 square plus 3 square. And finally, you have 52. So you'll get 55 square plus 3 square. And 49 square plus 3 square. The product of all of these terms is the denominator, right? And since you have a fraction where you have to divide the numerator by the denominator, notice there are many common factors. This gets cancelled here. 7 square plus 3 square is cancelled here. 25, 19 get cancelled here. Notice that everything is getting cancelled except 61 square plus 3 square in the numerator and 1 square plus 3 square in the denominator. These are the only two factors that remain. So our answer is basically 61 square plus 3 square divided by 1 square plus 3 square. Now 61 square will become basically 3721 plus 9 by this is 10. This is 3730 by 10 and our answer becomes 373. So pretty simple simplification. Once you have realized the main idea, which is factorization of x power 4 plus 4 times y power 4. If you correctly factorize it, you will be able to set the pattern and cancel off the terms. Okay. The next one is this one. Show that 7 divides 1 power 47 plus 2 power 47 plus 3 power 47 plus 4 power 47, 5 power 47 and 6 power 47. It's a pretty simple question. The idea is if a power n plus b power n has n as an odd positive integer, then by factor theorem, a plus b is a factor. A plus b is a factor of this because if you put a b is equal to minus a, this will get cancelled. So basically what we are saying is a plus b divides a power n plus b power n if n is odd and positive, right? So that means here the power is 47, which is odd and positive. So that means you can say 1 power 47 plus 6 power 47. A is 1, B is 6. So a plus b, which is 7, divides this, right? Similarly, 7 divides 2 power 47 and 5 power 47. And similarly, 7 divides 3 power 47 plus 4 power 47, right? So basically, 7 divides the whole expression because it divides all the parts of the expression grouped 2 at a time. So that is a pretty simple proof based on the idea that a plus b is a factor of a power n plus b power n, right? Let's look at the next problem. We have this one. Find all positive integers such that n square plus 1 divides n plus 1 divides n square plus 1. And a related problem, exactly same problem, but this time you have n square plus 2 divides n power 6 plus 206. So both of these problems. Now, if you have to check whether this is being divided by n plus 1, what we can do is write n square plus 1 as n plus 1 minus 1 whole square plus 1, right? This is the same thing, but I want to express it in terms of n plus 1, right? This is becoming n plus 1 whole square plus 1 minus 2 times n plus 1 plus 1, right? So this is looking like n plus 1 whole square minus 2 times n plus 1 plus 2, right? So now we have to check whether n plus 1 divides this expression. So it is clear that it definitely divides the first two parts of it. So if n plus 1 divides n square plus 1, it implies n plus 1 divides n plus 1 whole square minus 2 times n plus 1 plus 2, which implies n plus 1 should divide 2, which implies n should be 1. N plus 1 should divide 2 because it is already clearly dividing these two. So in order for the whole thing to be divisible by n plus 1, you have to have 2 is divisible by n plus 1. So n must be 1. In a similar fashion, we can try the other one also, n power 6 plus 206, and we have to check whether it is divisible by n square plus 2, right? So I want to write this expression in terms of n square plus 2. So how do I do that? I write it as n square plus 2 minus 2 whole power 3, right? This is the same expression, but now I'll write it like this: n square plus 2 whole cube minus 8 minus 3 into 2 n square plus 2 multiplied by n square plus 2 minus 2 plus 206. So notice that now it becomes n square plus 2 whole cube minus 6n square plus 2 plus 198, right? So for n square plus 2 to divide this, it is clearly dividing the first two parts of it. So therefore, n square plus 2 must divide 198, right? Then only it will work out. So that means n square must divide 196, right? And now, or we can directly say that n square plus 2 must be one of the factors of 198, which will be 1, 2, 3, 6, 9, 11, 18, 22, 20, 33, 66, 99, and 198. That is the possible values of n square plus 2, because these are the possible divisors of 198. Now from here we can say that n square can be basically 0, 1, 0, 1, 4 from here. N square cannot be 7 because it's not a perfect square. 9, 16, 31, 64, and 196. And from here we get n should be 0, 1, 2, 3, 4, 8, and 14. So these are the possible positive integer values of n for which you will have this expression. N square plus 2 divides this, right? So that is the proof of this one. One last problem, and possibly the most interesting problem, is this one. Let n and k be positive integers. We have to show that, first of all, for n is greater than equal to k, n by GCD of n and k divides nck. And second property is, for n is greater than equal to k, n plus 1 minus k by GCD of n plus 1 and k divides nck. Now in this problem, I'll show you a very interesting proof. But the property that the proof uses is this. So if GCD of A and B is, let's say, D, then we can say that GCD of TA and TB is the same as T times GCD of A and B, which will be same as T times D. This is the property that we will be using, okay? So what we are saying is GCD of TA and TB is T times the GCD of A and B, right? Where T is some integer. And that is basically T times D. So if you understand this property, which is fairly obvious, we'll be able to prove now these two results. So let's start off by saying we are going to calculate n times the GCD of nck and n minus 1 ck minus 1. This expression means n times GCD of nck and n minus 1 ck minus 1. So, okay, so we can take the n inside, and it is saying it's the same as n times nck is GCD with n times n minus 1 ck minus 1's GCD, right? We can take the common integer inside the expression, right, for GCD. Now remember, there is that identity NCK is equal to n by k, n minus 1 ck minus 1. This is a binomial theorem identity which can be easily proven. So basically from here we can say k times nck is equal to n times n minus 1 ck minus 1, right? And now here we have n times n minus 1 ck minus 1. So we can rewrite that as n times nck, comma, and this becomes k times nck, right? Using this identity. So notice that we have to take GCD of n times nck and k times nck, which is similar to nck is common integer here. Nck can be taken out and it is GCD of n and k, right? So what we have is this identity n times GCD of this is equal to nck times n GCD of n and k. So let me write that here, n times GCD of nck and n minus 1 ck minus 1 is equal to nck times GCD of n and k. So this means that n by GCD of n and k times GCD of nck and n minus 1 ck minus 1 is equal to nck, right? So notice that this is a GCD of two integers, GCD of two integers. So this is definitely an integer, right? So we have n by nc GCD of n and k multiplied by some integer is equal to nck, which proves that n by n and k GCD divides nck. So that is a nice way to prove it, very clever way to prove this. And you should understand this identity. This identity is valid for all n greater than equal to k. So this will be very handy later. Go through the proof again. Hopefully you will understand what we have done. And this identity is pretty valuable. Let's look at the second one. The second one also is done in exactly the same manner. We will start by calculating what is n plus 1 minus k times GCD of nck and nck minus 1. So we can take the n plus 1 minus k inside. So it is n plus 1 minus k times nck and n plus 1 minus k times nck minus 1. Now on the side, we will calculate what this expression is. This is n plus 1 minus k n factorial by n minus k plus 1 factorial k minus 1 factorial, which is, you can cancel this factor here. So this becomes n factorial by n minus k factorial k minus 1 factorial. Now since the sum of these two in the denominator is n minus 1, I should write it as n times n minus 1 factorial by n minus k factorial k minus 1 factorial, which means it becomes n times n minus 1 ck minus 1, right? This expression is equal to n times n minus 1 ck minus 1. And from the previous identity, we know that that is k times nck. There is an identity which connects nck and n minus 1 ck minus 1. The identity is nck is equal to n by k into n minus 1 ck minus 1. So therefore, n times n minus 1 ck minus 1 must be equal to k times nck. So what we have gotten is this expression can be written as n plus 1 minus k multiplied by nck, and comma, this is n times n minus 1 ck minus 1, which is k times nck. Now you have nck common here, so nck can come out, and it is the GCD of n plus 1 minus k with k. Now it is obvious that the GCD of this is the same as nck n plus 1 comma k, right? What are we saying? We are saying that nck GCD of n plus 1 minus k comma k is the same as nck GCD of n plus 1 and k, right? Because this is k doesn't affect the GCD because k is anyway divisible by k, right? When you take the GCD of this and this will be the same. This is same as Euclid's division algorithm. You can prove that GCD of this will be same as GCD of this. I will leave that to you. It's not a very difficult step, right? So what we have gotten is the initial expression n plus 1 minus k times GCD of nck and nck minus 1 is equal to, we are getting nck GCD of n plus 1 and k, right? So now we can say that n plus 1 minus k divided by GCD of n plus 1 and k multiplied by GCD of NCK and NCK minus 1 is equal to NCK, right? Now, this is an integer because it's a GCD of two binomial coefficients. So what we have showed basically is n plus 1 minus k divided by GCD of n plus 1 and k divides NCK. So it's the same kind of proof as the previous part, but we are able to establish it in a similar way using some binomial identities, right? So hopefully you have understood the techniques that we used in this video. These are some divisibility problems that I wanted to show you. There will be future videos containing more problems and more techniques. So keep watching. Also, by the way, there is a Maths Olympiad masterclass on Udemy that is available. It is pretty cheap right now. There's a discount going on. So if you are looking to get assignments and video lectures that cover all the topics of Olympiad maths, you should definitely buy that course on Udemy, and please put a review and check out the course basically. And if you like the course, please review it on Udemy. That's all for this video. I'll see you next time.